Hi everybody, welcome back to College Algebra, and today we're in section R.7 and we're going to be learning about radical expressions. So I'm going to show you how to use radical notation. I'm going to show you how to simplify radicals, at least square roots. We're going to do some operations with radicals, in other words, how to multiply, divide, add, and subtract with radicals. And then I'm going to show you how to rationalize a denominator and why that's necessary. So here we go. Now you will remember from section R.6 that in that section we learned how to use rational exponents to express roots. So remember, rational exponents just means the exponent is a fraction. But we can also express roots using radical notation. So here is a radical expression, and I just want to identify the different parts of it with you. First of all, the symbol itself, this symbol that looks like a division sign with a check mark on the front, is not really that, it's actually a radical. So the symbol itself is called a radical. The little number that's in the crook of the radical is called an index. And what this number does is it tells you which root you're taking, like are you doing the square root, the third root, the fourth root, etc. And then the number that's under the radical symbol is called a radicand. Together, the whole thing is called a radical expression. But we have three parts. We have the radical itself, which is just the symbol, the index, which tells us which root we're taking, and the radicand, which is the number we're taking the root of. So just to connect that to what we were doing in the last section, the nth root of a can also be written as a to the 1 over n. So do you see that the denominator of your rational exponent is just the index of your radical? They are the same thing. And if you have a to the m over n, then what you've got is a to the m under the radical, but the denominator of the exponent still represents the index of the radical. And there's also another way to write a rational exponent expression in radical form. You could also write it this way. You could say the nth root of a raised to the m is equal to a to the m over n. Now the only difference between these two is that with this one you would be doing the power first and then the root. And with this one you would be doing the root first and then the power. So if this is something that you're going to have to evaluate mentally, this is actually an easier way to think of it, because when you do the root, the number gets smaller, and then you can do the power. But on the other hand, if you have to do the power first, the number can get really large, and then you have to do a root of a really large number, and that can be awkward. So this first one's easier to write, but I like this second one because it's easier to do mentally. Now, I do want you to note that for square roots, we just write the radical without the index 2, and we just understand that the index is 2, because square roots, I guess, are the most common. So instead of bothering to write the 2 every time, if you see a radical that does not have an index, it's just understood to be 2. Also, note that since squaring a negative number gives a positive result, all positive numbers will have 2 square roots, the positive square root and the negative square root. However, the radical symbol always only indicates the positive one, which is also called the principal root. So for example, the square root of 9 equals 3. We would never say the square root of 9 equals negative 3, because the radical symbol always indicates the positive square root. Now, if you need to indicate the negative square root for any reason, you just put the negative sign in front of the radical. So negative square root of 9 would be negative 3, because square root of 9 is 3. However, the even root of a negative number is not real. Just as you saw in section R.6 where we couldn't find the even root of a negative number, here we also cannot do the even root of a negative number. So let's get started on example 1. We're going to be evaluating roots. Notice the instructions say write each root using exponents and evaluate. So the reason they want us to write it using exponents is because that will help you tie it back to what we learned in the last section, and that'll just make it easier for you to understand what we're doing if you had a good understanding of section R.6. So here in part A, we have fourth root of 16. So let's write that in exponential form first. So 4th root of 16 could be written as 16 to the 1/4 power. So in other words, we're looking for a number whose 4th power is 16, and of course that number is 2. In part B, we have 4th root of negative 16. So in exponential form, that would be negative 16 to the 1/4 power. So in this case, we would be looking for a number whose 4th power is negative 16. And of course, any real number raised to the 4th power is going to be positive. So this is not real. So again, notice that if you have a negative value under the radical, you cannot do an even root of a negative number. So that's always going to be not real. Here we have the negative 4th root of positive 16. So this index and this radical are only applying to the 16. Notice the negative is outside. So when I write this in exponential form, it's going to be negative 16 to the 1/4. Because there are no parentheses, I know that the 1/4 only applies to the 16, not to the negative that was outside. So now we need to evaluate this, and we know that the 4th root of 16 is 2, so we would say this is negative 2. In part D, we're looking for the 3rd root of 1,000. So in exponential form, that would be 1,000 to the 1/3 power. So we're looking for a number whose 3rd power is 1,000. Of course, that is 10. And in part E, we're looking for the 3rd root of negative 8. Now this is an odd root, so we are going to be able to evaluate it even though the number under the radical is negative. So we would say that the 3rd root of negative 8 is equal to negative 8 in parentheses to the 1/3 power. Notice I need the parentheses here to show that negative 8 is what's being raised. If you don't have the parentheses, then the negative would not be affected by the exponent. So the whole thing is supposed to be to the 1/3 power. And of course that means we're looking for a number whose 3rd power is negative 8. So that's going to be negative 2. Now let's look at example 2 together. And this one says write in radical form first and then simplify if possible. So we're still practicing making that link between exponent form and radical form. And notice that it says assume all variables represent positive real numbers. So we don't have to worry about any of our results being not real because all the variables that might go under a radical are going to be assumed to be positive real numbers. Okay, here we go. So in part A, we have 8 to the 2/3 power. Now I think at first it's going to be helpful for you to break this up into 2 separate exponents the way we did in the last section. So remember, 8 to the 2/3 power can be written as 8 to the 1/3 raised to the 2nd. Remember how we separated this exponent into 2 separate exponents? And the reason I wanted to do that is because now you can see that 8 to the 1/3 is going to be 3rd root of 8. And then this square will carry down here. So 8 to the 2/3 becomes 8 to the 1/3 raised to the 2nd. And that becomes 3rd root of 8 raised to the 2nd. Now let's see if we can work this out. We know the 3rd root of 8 is 2, so this is going to become 2 squared, and we know 2 squared is 4. Now in the last section, you learned how to do this really quickly. You learned how to say 3rd root of 8 is 2 and 2 squared is 4. So do you have to do all of this in order to know the answer? No, probably not. But what we are doing here is practicing converting from exponent form to radical form, just because you need that practice as you're getting used to how radicals work. Let's do the same thing on part B. So we have negative 32 in parentheses raised to the 4/5 power. So the parentheses are telling us that both the negative and the 32 are being raised to the 4/5 power. So first let's separate this into 2 separate exponents. So we're going to have negative 32 in parentheses raised to the 1/5 because 5 was the denominator of our exponent. And then that whole thing is going to be raised to the 4th. All right, now let's change this to radical form. So negative 32 to the 1/5 power is going to be written as fifth root of negative 32, and then we still want to raise the whole thing to the fourth power. All right, now let's work this out. So we're looking for a number whose fifth power is negative 32. And of course that number is negative 2, because 2 to the fifth is 32, and then a negative to the fifth power would still be negative. So the base is negative 2, and then we still have this exponent 4, and now negative 2 to the fourth power is going to be negative 2 times negative 2 times negative 2 times negative 2. If you multiply that all out, of course, you're going to get positive 16. So this one comes down to positive 16. On part C, we have negative 16 to the 3/4. Notice there are no parentheses, so this exponent does not apply to this negative. So the negative is going to just sit there, and our 3/4 is going to apply to the 16. Now let's separate this exponent into two exponents the way we did for these last two parts. So it's going to be 16 to the 1/4, all raised to the third. And again, notice that I put the parentheses around just the 16 to the 1/4, not the negative, because this exponent does not apply to this negative. Okay, now let's write this in radical form. So 16 to the 1/4 power would become the fourth root of 16, and that whole thing is going to be raised to the third power. And again, the negative is outside. So to simplify this, we'll say what is a number whose fourth power is 16, and of course that's going to simplify to 2. So we're going to have negative 2 to the third. And at this point I don't need the parentheses anymore because there's just one number here. So of course the exponent is going to apply to that number, and I don't need parentheses around the number to show that the negative is not included. Okay, so now 2 to the third power is 8, so we're going to have negative 8. On part D, we just simply have x to the 5/6 power. So again, we're going to separate this into two exponents. That's going to be x to the 1/6 raised to the fifth, and we're going to change this to radical notation. So x to the 1/6 becomes sixth root of x, and it's all raised to the fifth power. There's nothing we can do to simplify this, so this one's finished. So here in part E, we have 3x to the 2/3 power. Now notice there are no parentheses, so this exponent applies only to the x, not to the 3. The 3 will just be a coefficient that sits in front of our radical. Now, instead of writing this as two separate exponents the way we did on the last slide, now that you understand it a little better, I would like for us to kind of take a shortcut and just go straight to radical notation. So you know now that the denominator of the exponent becomes the index of the radical. So we're going to have 3 and then a cube root radical and x under the radical. Now what about this square? Well, this whole radical is getting squared. So one way to write this is to put parentheses around the radical and show that it's squared. So this is perfectly fine. There's nothing wrong with this. MyLabs Plus will accept this as your answer. But let's also remember that it can be written without parentheses. I don't know if you'll remember a few slides back when we first learned how to write rational exponents in radical form. We said this is one way to do it, but you also can write it where the square appears on the radicand. So we could write it as 3 times the cube root of x squared. So whether you do the root first and then the power, or whether you do the power first and then the root, it doesn't matter. They're both equivalent and they're both considered simplified, so they're both considered correct. Now on part F, we have 2p to the 1/2, and you'll remember that the denominator of the exponent becomes the index of the radical, but you also need to remember that when the index is a 2, we don't write it. So this is going to be 2 times the square root of p. So I want you to think about now, why is the 2 not under the radical? Because we don't have the whole thing in parentheses. So the exponent applies only to the p, so the p is the only thing under the radical. Here in part G, we do have parentheses. So we have parentheses 3a plus b, all to the 1/4 power. So in radical form, that's going to be fourth root of all of this. So fourth root of 3a plus b. Now here in example 3, we're going the other direction. So in this example, we're given the radical notation, and they're going to ask us to write each of these in exponential form. And again, we get to assume that the variables represent positive real numbers, so that just makes things easier on us. So first off, in part A, we have fourth root of x to the fifth. Now we're going to start by getting rid of this radical, and so you know that if we want the fourth root of x to the fifth, that's like saying we want x to the fifth raised to the 1/4 power. You see the index of the radical becomes the denominator of this exponent. And then we know by the power rule that x to the fifth raised to the 1/4 would be x to the 5/4, because 5 times 1/4 is just 5/4. In part B, we have the square root of 3y. Now since 3y is under the radical, the 3y is going to be the base of our exponential expression. So it's going to be 3y to the 1/2 power. Now remember, when there's no index showing, we know automatically that we can assume that the index is 2, because this radical represents the square root. In part C, we have 10 times the fifth root of z squared. So in this case, because the 10 is outside the parentheses, the only thing that this 2 is affecting is this radical inside. And you know that the 5 here is going to become the denominator of our exponent. So this is going to be 10 times z to the 2/5 power. In other words, 10 times z to the 2/5 power. In part D, this whole p squared plus q expression is all under a square root radical. So this whole p squared plus q is going to be raised to the 1/2 power. And really we cannot do any more simplifying to that because this is a sum. There's nothing we can do to simplify this exponent with this one. It just has to stay like this. Now let's talk about the product rule for radicals. In other words, we're going to learn how to multiply radicals together. Radicals that have the same index can be multiplied together using the product rule for radicals. So remember, we have to have the same index here. But if you have nth root of a times nth root of b, you can write that as nth root of a times b. So let's look at example 4 together. It says multiply, and again, we can assume that all variables represent positive real numbers, so that's good. All right, in part A, we have square root of 5 times square root of 7. Well, remembering the product rule from the last slide, we know that square root of 5 times square root of 7 can be written all under one radical. So that would be square root of 5 times 7. See how you just put them together under one radical? And then this is a multiplication that we can do. So square root of 5 times 7 becomes square root of 35. In part B, we have square root of 11 times square root of p. So if we put those together under one radical, we get square root of 11 times p, or just 11p. Now in this case, because the p is a variable, there's no way for us to simplify this further, so that's the final answer for this part. On part C, we have square root of 7 times square root of 11 times x, y, z. Now using the product rule for radicals, we know we can state this all under one radical. So underneath the radical, we're going to have 7 times 11x, y, z. And now we can multiply the 7 and the 11 together, and we'll have square root of 77 times x, y, z. Now we're going to talk about how to use the product rule backwards to simplify radicals. So whenever an answer contains a radical, we always should leave it in simplified form. Just like we simplify fractions at the end of a problem, we also should simplify radicals at the end of a problem. To simplify a square root radical means to write it so that there are no perfect squares under the radical. Now we're going to concentrate on simplifying square root radicals, but it works similarly for other indexes of radicals too. So if we had a third root, we would want to not leave any perfect cubes under the radical. And if we had a fourth root, we would want to not leave any perfect fourth powers under the radical. But because we're thinking about square roots here, We want to make sure that we don't leave any perfect squares under the radical. So like I said before, in order to simplify a radical, what we're going to do is use the product rule for radicals, but in reverse. So this is how it's going to go. If you wanted to simplify, for example, square root of 18, well, you would split the 18 into two factors, and you need to make one of them a perfect square. So if you think about the numbers that can be multiplied together to make 18, you might think of 3 times 6, but neither one of those is a perfect square. So let's go with 9 times 2. And again, I picked 9 times 2 because 9 is a perfect square. Now I'm going to use the product rule for radicals to split these up and give each one its own radical. So you know that if I have square root of 9 times 2, I can split these up and put each number under its own radical. That's just the product rule in reverse. So then we would have square root of 9 times square root of 2, and the square root of 9 is 3. So that would give us 3 times the square root of 2. And this is a simplified radical because the number under the radical does not contain any factors that are a perfect square. See, the point of simplifying a radical is that we want to leave the smallest possible number under the radical. This is a really important skill, so I hope you will practice with this and really get used to simplifying radicals. They're going to come up in several lessons later in college algebra, and things will always be easier for you if you understand how to simplify radicals. Just like you keep seeing fraction problems over and over in algebra, you're also going to keep seeing radical problems over and over. So let's practice simplifying these radicals. Here in part A we have square root of 24. So you need to think of two numbers that can be multiplied together to make 24, and you want one of them to be a perfect square. So you might think of 2 times 12, but neither one of those numbers is a perfect square. 3 times 8, neither one of those numbers is a perfect square. 4 times 6 makes 24, and 4 is a perfect square. So let's break our 24 down into 4 times 6. So the square root of 24 is equal to the square root of 4 times 6. Now we're going to use our product rule to split this up and give each factor its own radical. So that's going to be square root of 4 times square root of 6. And now we can simplify this radical because the square root of 4 is 2. So this is going to end up being 2 times the square root of 6. Now it's always important to look at the number left under the radical and make sure that it's as small as possible. So 6 is 2 times 3, and neither one of those numbers is a perfect square. So this is as simple as we can get this radical. So let's look at part B. Here we have square root of 108, and this number is a little larger than the two that we've done before. So the first thing you think of with 108 might be 9 times 12. That was the first number I thought of. And I like 9 times 12 because 9 is a perfect square. But as I look at this, I know that 12 also contains a factor that is a perfect square. I know that 12 is 4 times 3. So I'm going to go ahead and break down this 12 into 4 times 3. So that's going to give me 9 times 4 times 3. And now I'm going to use the product rule to give each factor its own radical. So that's going to be square root of 9 times square root of 4 times square root of 3. See, that's where our product rule comes in. And now we will simplify these first two radicals. The square root of 9 is 3, and the square root of 4 is 2, and the square root of 3 is not a whole number, so that number will stay under the radical. Okay, so now we have 3 times 2 times square root of 3, and of course outside the radical 3 times 2 needs to make 6. So our final answer is 6 times the square root of 3. Now, are there other ways that we could have done this? Yes, of course. We could have started out by saying that 108 is 2 times 54, and then you could break the 54 down into 9 times 6. There are lots of different ways you can go about finding an answer like this, but the most important thing is just take whatever number is under the radical and just start breaking it down. And what you're hoping for is to get perfect square factors under the radical. Now in part C, we have square root of 10. Now you know 10 can only be broken down into 2 times 5, or as I wrote it here, 5 times 2. And both of these numbers are prime, and so I don't have a perfect square under this radical, and that just means that square root of 10 is already in its simplest form, and that one cannot be simplified. Now in part D we have square root of 60. And my first thought here is that 60 is 4 times 15. So I'm going to say square root of 60 is equal to the square root of 4 times 15. Now use the product rule to write it as two radicals. And now we have square root of 4 times square root of 15. And the square root of 4 is 2. So this is going to be 2 times the square root of 15. Now if you check your 15, you know 15 is 3 times 5. And both of those numbers are prime, so there are no perfect squares now remaining under this radical, and this is completely simplified. Now let's do a little more practice simplifying radicals. So we have these three here, and I think it would be a good idea if you would pause the video and try them on your own. Do that, and then we'll go through them together. Okay, now we're going to go through these together. So first we have the square root of 32. Now my first thought was that 32 is 4 times 8, so I went ahead and wrote it that way. But then I remembered that 8 is going to be 4 times 2, so I broke the 8 down into 4 times 2. So now I have 4 times 4 times 2. So I have a pair of 4's here. So when I used the product rule to split this into two radicals, I didn't see any reason to split both of these 4's up into their own radical, although you certainly could. I kept them together, and then I put the 2 under its own radical. Now this pair of 4's here, 4 times 4, is actually 4 squared. So the square root of 4 squared is going to be 4. And then the square root of 2 is not a whole number, so that 2 is going to stay under its radical. And our final answer is 4 times the square root of 2. Now I do just want to mention to you that that's not the only way we could have done that radical. If we'd thought about it, we could have said that 32 was equal to 16 times 2. And then we could have split that up into two separate radicals, and the square root of 16 would have been 4. And so we still end up with 4 times the square root of 2. You can see that it doesn't matter which way you get to the final result. As long as the number you leave under the radical is as small as possible, everything will be fine. On part B, we have square root of 45. So probably the first pair of factors that comes to mind for 45 is going to be 9 times 5. And then we split this up so that each number has its own radical. And the square root of 9 is 3. And the square root of 5 is not a whole number, so that stays under the radical. And the final result is 3 times the square root of 5. Now I would encourage you to get a calculator and get a decimal value for square root of 45. And then calculate 3 times the square root of 5, and notice that they have the same decimal value. So that's one way we can verify that we did this correctly, is we can compare decimal values. But notice that when we simplify radicals, we leave them in radical form. We never go to decimal form, because in algebra we like everything to stay exact. And if you go to decimal form, you're going to have to round off at some point, and we just don't want that. Okay, let's look at part C. So we have square root of 300. Now, you could say that 300 is 100 times 3. That would be probably the fastest and easiest way. But I was thinking that a lot of you might look at 300 and think, well, that's 30 times 10. And then 30 could break down into 3 times 10. So 300 broke down into 30 times 10, and then 30 broke down into 3 times 10. So notice that 3 times 10 times 10 does equal 300, so far we're in good shape. Now when I split this up, I'm going to put my pair of 10's together under one radical, and I'm going to put the 3 under a separate radical. And of course, 10 times 10 is 10 squared. So the square root of 10 squared is just 10, and then the square root of 3 is not a whole number, so that stays under that radical. And so the square root of 300 is equal to 10 times the square root of 3. Okay, now I'm going to show you how to simplify radicals that have variables in the radicand. And in order to do that, we're going to have to think a little bit about whether the number that the variable represents is positive or negative. Now remember, when we first looked at the radical symbol, we said that a square root radical has to represent a positive value. So when we think about the square root of x squared, we know that whatever we have over here on the right has to be positive because the radical always represents the positive square root. So this is asking us to find a number that when you raise it to the second power, you get x squared. So of course that number is x, but in order to force this to be a positive, we need to put absolute value bars around it, because x could represent a negative number, and if that were the case, then we would have a radical equal to a negative, and we can't let that happen. So we have to force this to be positive by putting the absolute value bars around it. So again, the absolute value bars are necessary to make sure that we get a positive value in case x represents a negative number. This is always the case with an even index. So if you're doing square root, fourth root, sixth root, this absolute value thing is always going to come up. We have to make sure that an even index radical always represents a positive number. But if the index is odd, like if you're doing third root, fifth root, etc., then the result can be either positive or negative, so in that case we would not want the bars. So again, this only comes up when we're doing an even root. It does not happen when we're considering an odd root. So let's look at example 6 together, and the instructions just say simplify. So we'll apply the absolute value bars whenever we need to, but then if we can drop them at the end and still be guaranteed a positive number, then we'll do that. So let's start out in part A looking at square root of x to the fourth. So first of all, we need to notice that we're doing an even root, so we are going to need the absolute value bars. So now we need to ask ourselves, what is a number that when you raise it to the second power, you get x to the fourth? Well, x squared to the second power would be x to the fourth. So we're going to have x squared inside the bars. So now we have absolute value of x squared. And remember, the purpose of the bars is just to make sure that we get a positive value here. But think about it. It doesn't matter whether x is positive or negative, because it's going to get squared. We're going to get a positive here anyway, even without the bars. So in this case, we actually can just drop the bars. It's not that they don't belong here, it's that we have an even power still left, and so the negative thing is just not going to come up. So we drop the bars because they end up not being necessary. Here in part B, we have cube root of p to the third. Now this is an odd root, so we don't need the bars at all. P can be positive or negative, and we should let it be whatever it's supposed to be. So now to simplify this, we say, what is a number that you can raise to the third power and get p to the third power? So of course that number is p. And if p to the third is negative, then p will be negative. And if p to the third is positive, then p will be positive. So this is fine as is, and we do not want the absolute value bars here. If you look at part C, we have sixth root of m to the sixth. So again, this is an even root, and we will need the bars. And now we say, what is a number that you can raise to the sixth power and get m to the sixth? And of course that number is m. Now in this case we will have to keep the bars, because if m is negative, that's a problem. We need to make sure that whatever we get as our final answer is positive. So we have the bars here to make sure that happens. You see how that's different from over here? Over here we had an even power of x, and so it was going to come out positive no matter what. We don't have that kind of guarantee with m, so we do need the bars here. And then on part D we have square root of 16 m to the 8th r to the 6th. So because this is an even root, we will need the absolute value bars around our variables. And let's just take this one factor at a time. The square root of 16 is 4, because 4 to the second power makes 16. The square root of m to the 8th is going to be m to the 4th, but because this is a square root and this is a variable, I'll need to put that in absolute value bars. And then the square root of r to the 6th is r to the 3rd, but again, this is an even root, so I'll need absolute value bars. And now let's look at both of these sets of bars and decide if we can do away with either one of them. So 4 is positive, and we write it as a positive number, and that's fine. M to the fourth is going to be a positive number no matter what, because whether M is positive or negative, by the time you raise it to the fourth power, you have a positive. So I really don't need the bars there. I'm going to get a positive here no matter what. But on R to the third, 3 is an odd power. So I do need the bars to make sure that this comes out positive, because if R is negative, then R to the third would be negative, and then I would need to force it to be positive. So I will keep the bars around that part. Now, if we could know in advance that all the variables represent positive numbers only, then we wouldn't even have to worry about the absolute value bars, because there would never be a danger of getting a negative result. So, when you're simplifying square roots, watch out for instructions that say assume all variables represent positive numbers. If the instructions say that, then we no longer have to worry about the absolute value bars. So whenever you read these instructions, just know that they're trying to say, hey, don't even worry about absolute value bars for this problem. Now, as you've already seen, if you have a variable raised to an even power, it's easy to get the square root of that by just cutting the power in half. But if you have an odd power and you need to take a square root of an odd power, then there's a little trick that we use. So when you're simplifying square root radicals that contain variables, you can separate the variable into two factors, an even one and a first power. And then what happens is it's easy to take the square root of the even power, and the first power just stays under the radical. So here is an example for us to look at. Let's think about square root of x to the 7th. Okay, this is an odd power. So the easiest way to get the square root is to split this up into x to the 6th times x. You see there's an even power, and we want that because it's easy to take the square root of an even power. And then this is the odd power here. You can see that 6 plus 1 would be 7. So this radical is equivalent to this one. And now we're going to use the product rule to split this up into two radicals. Okay, now we want the square root of x to the 6th. And of course that's going to be x to the 3rd. But we don't have instructions here that say that all variables represent positive numbers. So we have to think about how can we make sure that the square root of x to the 6th comes out positive. So we know it's x to the 3rd, but we're going to put that in absolute value bars to make sure that it's positive, and then it's going to be multiplied by this square root of x, which we can't get out from under the radical. So here is example 7, and let's simplify. And look, this time the instructions say assume that all variables represent positive numbers. And you know the translation of that is just don't worry about absolute value bars here. Okay, so in part A we have square root of 16 m to the 3rd. Now it's going to be pretty easy to do the square root of 16, but m to the 3rd is an odd power. So let's split that up into 16 times m squared times m. You see how m squared times m is still m to the 3rd, but we just split it up so that it's an even power and a single power. Okay, now we can use the product rule to give each factor its own radical. So we're going to have square root of 16 times square root of m squared times square root of m. Now the square root of 16 is 4. And the square root of m squared is m. And we normally would have to put the absolute value bars, but because they gave us this little instruction here that says we can assume all the variables are positive numbers, that means we can do away with the absolute value bars. And then square root of m is going to be here, and we cannot get that m out from under the radical. Okay, now let's go on to part B. Here we have square root of 2000 k to the 7th q to the 8th. So in this case, I'll need to break down the 2000 as well as the odd power of k. Now you might think about 2000 as 2 times 1,000 or even 20 times 100, but I chose to think about 2000 as 400 times 5 because 400 is a perfect square. 400 is 20 times 20. Okay, now k to the 7th is an odd power, so I need to split that into k to the 6th times k. And then, of course, q to the 8th is an even power, so it doesn't need to be split up at all. Now, we're to the point where we've used the product rule so often that I think you know that this step happens, and we don't really have to write it out every time. You can write it out if it's helpful to you, but I'm going to give you permission to skip that step at this point and just take the square root directly. So the square root of 400 is going to be 20. And then the 5 does not have a whole number square root, so it's going to stay under the radical. The square root of k to the 6th is k to the 3rd. And the k is a single power of the variable, so that's not going to come out from under the radical. And then the square root of q to the 8th is q to the 4th. Okay, so there is everything we could take the square root of. And now we need under the radical, the 5, and the k. So our final answer here was 20k to the 3rd q to the 4th times the square root of 5k. Okay, on part C, we come back down to earth with a little smaller number. So we have square root of 72 times x times y to the 3rd. Now you're probably like me, and when I see 72, my first thought is 8 times 9. So as I break the 72 down, I'm going to first write it as 8 times 9. And then I have times x and times y to the 3rd, but y to the 3rd is an odd power, so I'm going to break that down into y squared times y. Now before I start working on taking square roots, I noticed that 8 contains a perfect square factor because 8 is 4 times 2. So I'm going to go ahead and break the 8 down into 4 times 2, and I'm going to keep the 9 and all the rest. And now let's find the square root of each factor that's a perfect square. So the square root of 4 is 2, and this 2 is going to have to stay under the radical. And the square root of 9 is 3, and this x is going to have to stay under the radical. And the square root of y squared is y. Okay, now everything that we didn't already use is going to have to stay under this radical. So 2 times x times y is under the radical.